Let's talk about power. What does it mean in physics? Well, let's start by thinking about this. Let's say we have two people, and they're going to push a box. They each have a box. The boxes are identical. And they're going to push the box at a constant velocity. Each of them is going to push at a constant velocity. And they're going to push, let's say they're just going to push at a constant velocity. So let's say this person pushes at V1, because they're person number 1, and this person pushes at V2, both constant velocities. And let's say that V2 is greater than V1. Well, the force, if they're going to push at these constant velocities, assuming it's the same box, same frictional force, all that, forces F1 and F2 are equal. So there's an exclamation point at the end there. Can you see that? Yes. Because that's exciting. So that's fine. We know that if something's moving at a constant velocity or if it's at rest, that means we have an equilibrium condition, which means all the forces are balanced. So, excuse me. So that's fine, but we would like to be able to somehow make a nod to this person too who's pushing faster. So here the forces are equal. What about work? What about the situation where, like, what does the concept of work do for us? So work really recognizes here that with the same velocities here, pushing at V1 and V2, if person 1 pushes at a distance D1 and person 2 pushes at a distance D2, well, the forces are equal, but now the work done by person 2 is greater than the work done by person 1 because these are constant forces. The work is equal to force. Those two are equal to each other, F2 and F1, but D2 is greater. F2 and F1 are equal, but D2 is greater than D1. So we now have a way of making a nod in terms of like these different physical quantities that we're going to assign to things. We have a way of recognizing that this person, even if this person was pushing faster, if they stopped, this person did more work because their constant force pushed it through a greater distance. Still, that doesn't help us with the situation of somebody pushing faster. So now, let's say we have the two people push the box, and now they're going to push it the same distance, D. But this person is still pushing at V1, and this person is still pushing at V2, so this person 2 is going to get it there faster. So what are we going to do now? We're going to say, we're going to define power is the rate of energy transfer. Rate, what does that make you think of? Rate of, and what is the mechanism that moves energy around? Well, that's work. So you could say it's the rate of work. So So there's different ways that we can write this. We could say that power is equal to, if you just wanted to talk about average power, then you could say that power is the change, the amount that the energy changed over delta T, and that's the amount of energy change, that's usually equal to the amount of work, right? So that's two different ways of writing that. And if you wanted to know instantaneous power, that is equal to, instead of having delta E over delta T, you're a calculus student, this is like an average slope. So if you wanted to know the real thing, like right at some instant, then it'd be dE dt, or you could write that as d work dt, same thing. And then there's one other way of writing this. Let me move on to a new sheet. Oh no, that's got some other stuff on it. Oh, that's old stuff. Let's see. I need some more paper. What am I going to do? I'm just going to go get some more paper. Let's see. I think this looks like something old. What's this? Okay. So if, let's see, we have power is equal to d work dt. And what is work equal to? Well, work is equal to force times distance. So and the derivative, if for a constant force, the derivative of position, sorry, that's a d, that means like that we're taking the differential, like derivative kind of d, and that's d for distance. So derivative of distance with respect to time, if that force is constant, then that is going to be force times, let's see, what's the derivative of distance with respect to time? That's velocity. So this is another way of writing that. Now, someday you're going to get a glimpse, I think actually someday pretty soon, for the next assessment that we have, you're going to get a look at the College Board equation sheet, and we'll start using that as a reference during assessments and in general. And you'll see that they have the, I'm just going to leave it like this for us, because almost always we use this in just one-dimensional motion problems, so it's not an issue for us usually when these are vectors that are not pointed the same way. But if it is in fact the case that they're not going exactly the same way, then it's just like work. It's force times velocity times the cosine of the angle between them. I'm not going to make a big deal about that because in the kind of problems that we're going to see, it is almost always, I'm trying to think of one single problem that I'm going to throw at you where they're not going in the same direction, and I can't think of one. So there you go. So on the little College Board sheet, you're going to see that these two versions of it. Power is the rate of change of energy with respect to time, and you're going to see that power is equal to force dot velocity, which just means force times velocity if they're pointed in the same direction. Right? It means that. All right, that's power. Let's try some problems.